Hello there. I hope you're having a good AGU online everywhere. Today, I want to talk with you about a little bit of the work that I've been developing at NASA JPL, where we try to consider the effects of canopy structure on hyperspectral radiative transfer and the impacts of that on global photosynthesis. So I would like to start with this question: will the land surface remain a carbon sink by the end of this century? And the way in which Earth system scientists try to address this question is by running Earth system models, these very large models that represent the Earth system. And here I show you three plots where the authors show the global carbon land uptake from the beginning of the Industrial Revolution until the end of this century. And as we can see, all the members of the CIMIP ensemble members have a high disagreement, not only on the magnitude, but also on the sign of the land uptake by the end of this century. Well, these models disagree a lot among themselves because they represent different things usually, and they are parameterized in different ways. But the IPCC report also calls out for the fact that these models represent the transfer of radiation, water, and momentum very simply. And that is because these models have to be run over large areas for very long periods of time. However, mounting evidence suggests that canopy structure, or the 3D nature of vegetation architecture, is important for radiative transfer, and it has impacts on local and global photosynthesis. So how do these models calculate radiative transfer? Well, first of all, they have to make assumptions about the structure of these canopies. So usually these Earth system models have a representation of canopy structure that looks a lot like that one. So it's a cloud of randomly distributed green dots, where the leaf area index is the optical depth of this vegetation canopy. And so the dimension that these radiative transfer schemes account for is the vertical dimension. And so there's also the fact that these models usually calculate radiative transfer in two broad bands: the photosynthetically active radiation, or PAR, and the near infrared, or NIR. The PAR radiation is associated with photosynthesis, is the energy that plants use to photosynthesize. And the near infrared has impacts on the surface temperature. And so these models output the radiation partitioning. And we can think of the radiation partitioning as part of the radiation is absorbed by the canopy and impacts photosynthesis. Part of this radiation is reflected back to the atmosphere, impacting the surface energy budget. And part of this radiation is transmitted through the canopy, interact with the background soil albedo underneath. When we think about radiation partitioning, we're talking about these three terms of the radiation. Now, a simple exercise we can make to evaluate if the homogeneous case or the 1D canopy case is a good enough approximation in terms of considering canopy structural differentiation in these canopies is running 3D radiative transfer models. And so in this exercise here, I use the 3D radiative transfer model MyESPA, and I hold the leaf area index constant and equal to 1.5 meters squared per meter square. And all I do is vary the canopy density. So the way in which the 3D model sees it is a number of spheres randomly distributed over the space, and we vary the canopy density from a very sparse case to a dense case. When we look at the results of this canopy in comparison to the 1D case, where we call it two-stream, we see that for the fraction of absorbed photosynthetically active radiation across all sun-zenith angles, and including when the radiation is completely diffuse or isotropic, we see a large bias in the amount of absorbed and also the amount of reflected radiation to the atmosphere. And that has a lot of implications for the accurate calculation of photosynthesis and the surface energy balance. A way in which our system models try to go around the fact that these radiative transfer schemes don't represent the 3D nature of vegetation canopies is by adding an index called the clumping index. So the idea behind the clumping index is this index that we multiply the true LAI by, and we get an effective LAI in radiative terms. Or in other words, this clumping index tries to modulate the optical depth of the vegetation canopy in order to account for the three-dimensional nature of the radiative transfer. So we might ask, is there a value or a combination of values in which we can multiply true LAI by in order to get the same result as more accurate radiative transfer schemes? And this parameterization scheme has been tested with local gross primary productivity. So in this exercise here, we use direct transmittance from digital hemispherical photographs and from accurate 3D modeling to derive a clumping index. And when we apply this clumping index into a land surface model of an Earth system model, in this case, joules, we can see that we correct or we improve the agreement between model GPP and observed GPP with flux tower data. Likewise, if we perform the same exercise, but now for the whole globe, we also see an improvement with observations. So in this exercise, we use clumping index derived from MODIS, and we use the land component of the UKSM, the British Earth System model, and we compare that, the global GPP from the Earth System model with the FluxNet MTE GPP. And we get a better agreement with the data, especially over the tropics, where the vegetation is very dense and the LAI values are higher. So the way in which these models work, these our system models usually work, it's an ultra parameterized model. So they usually have the paradigm of plant functional types to describe the land surface, but also they have the idea of lookup tables to describe spectral properties of this canopy. So when we think about a new generation Earth system model like CliMA or the Climate Model Alliance, we are really thinking about an Earth system model that uses Earth observation to drive these Earth system models. And moreover, we want to learn from this data. So we really want to move away from the ultra parameterized Earth system model into an Earth system model that can assimilate data at the same time and come up with results and predictions. So instead of having a lookup table for spectral properties of the canopy, we want to calculate the spectral properties from biochemical components of the land surface, like chlorophyll content, for example. Another way that we want to move away from is the idea that the radiative transfer scheme has to be resolved in two broad bands. We want a radiative transfer scheme that is instead hyperspectral, so we can be directly comparable to observed data. And we also want an Earth system model that has that predicts variables like sun-induced fluorescence, that has been used as a proxy of GPP to an extent, and it will be amazing to have an Earth system model that already calculates stuff in order to be directly compared to Earth observations. And we want to do all that, including the vertical and the horizontal canopy heterogeneous structure. And so the idea behind this Earth system model is that nowadays we live in a very exciting era where we have many variables that before were simply measured from flux tower data from for a single site on Earth, to a whole Earth coverage with new instruments on board of satellites and the International Space Station. So the idea of having an Earth system model that actually calculates hyperspectral radiative transfer is to be directly compared to new NASA missions like the SBG, for example, that will measure the shortwave radiation spectrum hyperspectrally instead of two broadbands. So the question is, so can we use now the same clumping index parameterization scheme to account for three-dimensional heterogeneity of canopy architecture, but hyperspectrally now, instead of solving the problem for two broadbands? And so to test that, we use a model benchmarking exercise called the RAMI for PILPs, where the authors of the RAMI for PILPs recreate a number of canopy scenes with different LAIs, different soil background albedos, different sun zenith angles, and different sensor geometry, and calculate all the radiation partitioning for this scene using ray tracer, so a very accurate 3D model. And here I show one example for the LAI, for the canopy with LAI equals to 0.5, so black soil albedo and sun zenith angle equals 27 degrees. But as we can see, the blue lines of all three members of the radiation partitioning represent the CliMA Land radiative transfer model without clumping. And when we add clumping, we move this curve to the yellow curve that show a much better agreement with the reference values or the 3D model values that are calculated from this ray tracer model, represented by the black crosses and the black dashed lines. And so when we sum up all the canopy scenes with all LAIs, all sun zenith angles, all soil backgrounds albedo, we actually get this scatter plot. So the blue line represents the model without clumping, and the yellow lines represent the model with clumping. So we can see a much better agreement with the reference values by an increased value of R square and a decreased value of root mean square error. So I just want to finish this talk showing you a preliminary validation exercise that we did for sun-induced fluorescence. So we use SIF measure from the recently launched OCO3 on board of the International Space Station over Nile Ridge. And we calculate SIF from this model and compare with the OCO3 data using a version of the model with and a version of the model without clumping. And what we can see is that when we add the clumping index from MODIS for Nile Ridge, we improve the agreement between model SIF and measure SIF from OCO3. This is exciting somehow because it indicates that for a correct derivation of SIF, we might have to include information about the canopy structure as well. So I would like to thank you very much for your attention, and please reach out on my email. And you can also add me on Twitter at Renato Braghiere. I wish you a very good AGU Online everywhere. Thank you very much.